Hello, everyone. So today we're going to be focusing a lot more on the actual nature of packets of light. So far, we've talked a lot about how energy states are quantized and separated into discrete energy levels. And light is essentially the means of providing that energy to move in between these discrete energy levels. Now, one of the important things is what this does is it indicates that light exists in discrete packets of energy, but it doesn't definitively prove it. And one of the reasons why this is an important distinction is because, again, quantum mechanics really can has a lot to owe to Planck for first establishing quantization of energy. But he didn't ever believe in quantum mechanics. And as a result, he was very reluctant about making any assertions of his data. So what's important to remember is that as developed by Planck, what we have is the energy in light is given by Planck's constant and the frequency of the involved light. And then there was essentially this scaling constant, which was known to be an integer, n. These days, we call this the number of photons, where photons are discrete particles of light. So this means that light itself can actually be quantized and it delivers a set amount of energy per photon. And one of the reasons why this is very important is when we start talking about processes that require energy, especially energy delivered by light or released by light, it means that we can occasionally have some mismatch issues. One of the biggest demonstrations of this is if we're trying to match out the energy a reaction needs with the energy available by light, by the given wavelengths of light that we're trying to use. One of my favorite examples, because I'm an energy guy, is solar energy. So, one of the ultimate goals of the green energy movement is to try and use solar energy to convert water into hydrogen and oxygen. So, this is called more colloquially known as water splitting. So, to take two water molecules, I split it into two hydrogen molecules and one oxygen molecule. Now, this is, of course, going to require a significant amount of energy. Specifically, it requires about 8 times 10 to the negative 19th joules per mole of oxygen produced, or per 2 moles of water consumed. Now, one of the issues of this is that we can try and drive this through electrochemical processes, but it would make a lot more convenient if I didn't have to set up full electrochemical cells, if instead I could just power it as a photochemical reaction. So more or less act like a plant, absorb some green light, which is at about 550 nanometers, drive the reaction. Well, the question is how many photons is this going to require? Because each one of these photons is a separate absorption event. And if I have one photon, it's easy. If I have two photons, I need to actually coordinate those two absorptions. 3 or 4 becomes trickier and trickier. Plants have whole apparati to channel the absorption of photons. Humans were not quite so good at making those sort of structures. So this is a very important question. So what we can do is first of all, figure out what the frequency uh, of light, the frequency of a 550 nanometer light is. So again, convert our wavelength to frequencies using the speed of light, comes out about 544 terahertz, so a fair bit of energy. Then I can convert this into the energy of light using E equals h nu. So it's about 3.6 times 10 to the negative 19th joules. This is slightly problematic as I require 7.9 more or less. So it turns out that this requires 2.2 photons. Well, that 0.2 is really annoying because I can't deliver a fraction of a photon, which means this process requires 3 photons. So in reality, I'm going to need 3 photons to deliver enough energy to drive this reaction. It gives me a little bit of extra, not too bad. Unfortunately, because each one of these processes is plagued by efficiency issues, in reality, we typically use 4 photons, which actually works because 4 photons corresponds to the 4 electrons being transferred. It's worth noting that in nature, this process is driven by 8 photons, but it also works by some of those photons being high energy and some of those photons being in the red region, so being much lower in energy. Not to mention, they aren't just driving this simple reaction, they're also driving the production of glucose, which again gives a little bit more complicated, is a little more complicated and thus needs a little bit more energy. However, all of this idea of photons, while very useful as we see here, wasn't actually conclusively proven until Einstein came on the scene. Not too surprising because 1905 is known as the wonder year for a reason. Einstein delivered 4 groundbreaking papers. As we already saw, he delivered one paper on heat capacity, another paper on photoelectric effect, a third paper founding statistical mechanics, and a fourth paper establishing uh, special special relativity. So he only managed to found 3 separate branches of science in a single year. So not doing too bad. So like black body radiation, the photoelectric effect was considered one of the great mysteries of classical physics. So the idea of the photoelectric effect is that if I go ahead and I hit a metal surface with light, we tend to see a fun kind of behavior. As I increase the frequency of light, I increase the energy of electrons that I can essentially kick off of the metal. So again, this makes sense. We saw with Planck's equations that increased frequency means increased energy. Now, what gets kind of interesting is, not too surprisingly, you increase the intensity of the light, but when you increase the intensity of light, you don't increase the energy of the electrons coming off. Instead, you only increase the number of electrons coming off. Well, this never quite made sense to classical physicists. And then there was the real burning question that no one was ever able to explain, which is that all of this linear relationship, which is beautiful, only exists above a certain threshold frequency. Above this threshold, I increase the frequency of radiation, I increase the kinetic energy. But below this threshold, I get nothing. I decrease my frequency below this threshold and no electrons whatsoever are produced, no matter how intense the light is. And one of the reasons why this is was very confusing is intensity of light gives us the total energy of light. But as we've seen before, it's not the total energy of light that actually matters. It's the energy per photon. And we can essentially explain this whole idea of the photoelectric effect by simply saying it doesn't matter if I have 10 photons hitting a metal. All that matters is the energy in a single photon. So this means that the energy incident is just h nu. 1 photon, no integer value out here. We're looking at a single photon event. Then I can go ahead and predict the kinetic energy of the electron coming off the metal simply using classical physics. E equals mv squared, mass times velocity squared, where again, the mass is the mass of our electron and v is essentially the velocity of the electron coming off. And additionally, one of the tricks here is that this electron requires a minimum amount of energy, and this is going to be called our work function. This is related to our threshold frequency to cause any ejection of the electron from the metal surface. So this can essentially be framed in this idea of energy in equals energy out. So the energy coming into the system is essentially h nu. This is how much energy my photon has. My energy out comes in 2 forms. First, I have to put in a certain amount of energy to kick out the electron. This is essentially how much energy it takes to remove the electron from the metal surface. This is really what my work function is telling me. Any additional energy is going to go into the kinetic energy, which again, as we see here, means that it's more or less just going into the velocity. And again, I do desperately apologize that we don't have enough V's in physics. Here, V is velocity and nu is Frequency, unfortunately, you can't actually tell the difference. So I am sorry, I apologize, and watch out. But where this actually becomes really important is back to how what phenomena was being experimentally measured. And that was indeed the kinetic energy through essentially the velocity or momentum of the electron coming out. So what we have is the momentum of the electron is going to be given by h nu minus the work function. And here's that tricky thing. Because since I can't have a negative kinetic energy, this means I'm going to have no electron being produced if h nu is less than the work function. As soon as h nu is greater than the work function, I emit electrons and I'm going to have a linear relationship. And this is essentially just going to be my intercept. So this is essentially a really important sort of phenomena, partially because it illustrates photoelectric effect, and also partially because it really illustrates that electrons are held into systems by a given amount of energy. And for, again, a nice solid like a metal, it's quite nice and straightforward. It gets more complex for more complex systems. So we can try and use these basic ideas to look at other similar to effects that are very similar to the photoelectric effect, like trying to analyze a simple solar cell. So let's say I've got a silicon solar cell. Silicon has a work function about 4.85 eV. So I want to try and figure out what's going to be my threshold frequency of light in order to generate a current, more or less to kick an electron out of silica. So in this case, we're going to want to start by figuring out what our work function is in terms of joules, because that tends to be the numbers that we work in best. So we can go ahead and convert our work function from EV to joules. It's about 7.8 times 10 to the negative 19th joules. The next feature is to try and figure out the frequency of light essentially required to eject an electron. In this case, it's about 1.17 times 10 to the negative 5th. Again, going from joules to frequency. One way you could do is reset essentially the kinetic energy to 0 and rearranged our work function equation. Then we can turn that frequency into wavelength, and through some simple analysis, watch your units, turns out that this is about 255.6 nanometers. Congratulations, this is UVB light. This is also one of the reasons why UV light can be so dangerous, is it can actually ionize atoms, including those in your cells and DNA. But it's worth noting that we know we can generate electricity from a solar cell at much higher wavelengths, with much lower energy. Now, the reason why is essentially some features of we aren't just trying to kick out electrons into the ether. We're raising it from one energy level to another energy level, slightly lower than just sheer vacuum. And it's essentially the introduction of this conduction band, a lower energy level where the electrons can be swept away from the surface, that really allows solar cells. So it's a little bit more complex than photoelectric effect. But that said, please don't go exposing your silicon to UV light, because you're going to ionize it. So one of those things that's kind of fun to watch out for. So this ends up building up a nice basics of quantum mechanics principles. We're going to start taking these basic principles of photons and photoelectric effect and start applying it to the introduction of studying how all matter behaves as waves. Till next time, take care.